Good morning. Welcome to the lecture series on digital electronics 18EC 302C. In today's lecture, we are going to learn an important combinational logic circuit, that is decoder. So, the outcome of this lecture will be to define what is a decoder, and in particular to understand the working of 3 by 8 decoder, and to write the truth table of the same, and to draw a combination logic circuit of the 3 by 8 decoder. And also the student should be able to mention any applications of decoder IC. So we'll start discussing about decoders. So what is a decoder? Or what is meant by code, or what is meant by decode? So we have seen a number of binary codes previously, and you can see that a binary code of n bit can represent up to 2 power n distinct elements of the coded information. For example, if I have a binary code of only 1 bit, then it can represent two different elements. One is 0, other is 1. Similarly, if I have a binary code of 2 bits, then it can represent 2 power 2, that is 4 distinct elements of the coded information, and they are 0 0, 0 1, 1 0 and 1 1. So here we can show that so we have only 1 bit code, 1 bit code, then we have two distinct elements, 1 and 0. In the same way, if we have 2 bit code, we have 4 distinct elements, 0 0, 0 1, 1 0, 1 1. Similarly, if we have, that means 4 means it is 2 power 2. And in the same way, if we have n bit coded information, then they represent 2 power n distinct elements. 2 power n distinct elements. So that is, a binary code of n bits can now represents up to 2 power n distinct elements of the coded information. Then how to identify the distinct elements from the n bit code? So to identify what the code exactly represents, or which element the code n bit code actually represents, we require a combination logic circuit. And for that combination logic circuit, have n input lines, so that these n bits can be applied as input, and it has 2 power n output lines to show that which element is represented by that n bit input code. And this circuit will be calling it as decoder, since it is decoding the information present in n bits. So I can also say that a decoder is a combination circuit that is converting n bits of binary information of input lines to a maximum of 2 power n unique output lines. Or otherwise I can say that it is detecting the presence of the code or a specific combination of bits on its input, and it indicates the presence of that code at the output by making the specified output level active. So that is just it is detecting what is that code that is present at its input lines. So for this, the decoder has, you can see that a decoder has n input lines to handle n bits of code, and from one out of the 2 power n lines to indicate the presence of one or more n bit combination. That means for one combination of input, the output is indicated on one out of the 2 power n output line, and for a different n bit combination at its input, the other line is used to indicate the combination at the output out of 2 power n. So in the same way, so since we have n bits, there can be 2 power n combinations. So indicate each of these combinations, we have 2 power n output lines. So sometimes decoders are designated as an n to m line decoders. N to m line means n number of inputs and m number of output lines. So then it is called as n to m line decoder, where I can say that m, or when n is the number of input lines and m is the number of output lines, where the maximum value of m can be is 2 power n. So the output lines should not be, may not be exactly 2 power n in for all the decoders, maybe less than 2 power n also. So this is how we define a decoder. So decoder is a combinational circuit which converts n bits of information or detects n bits of code present at its input lines and indicates the presence of that unique code at the by using one out of the 2 power n output lines. So now this is what is a decoder in general. So we can have different types of decoder depending on the value chosen for the code or the number of bits present in the code that is applied at the input of decoder. So if it is 1 bit, if only 1 bit is applied at the input, then it becomes 1 to 2 line decoder. So if the number of output lines are 2, then it is 1 to 2 line decoder, and if n equals 2, then and if m equals 4, then it is 2 to 4 line decoder, or 2 by 4 decoder. Anyway, we can call it as 2 by 4 decoder or 2 to 4 lines decoder. In the same way, if n equals 3, that means the code that we apply at the input of decoder has 3 bits, then n equals 3. Then if m equals 2 power n, that is 8 output lines. So 3 input lines and 8 output lines. So this can be called as 3 to 8 lines decoder, or simply 3 by 8 decoder. So as per syllabus, we will discuss in detail the working of this 3 by 8 decoder. So as we have seen, the 3 by 8 line decoder, 3 to 8 line decoder or 3 by 8 decoder, both are same. So consists of 3 input variables and 8 output lines, or 3 input lines and 8 output lines. So the 3 inputs are decoded into 8 outputs, because when you use a 3-bit code, it has 8 different combinations. So then it can be decoded into 8 outputs. So each output representing one of the combination of the 3 input variable. And here you can see that one combination of the 3 input variable, as we have seen, it is also called as a minterm. So each output represents one minterm of the 3 variables. So I can also say that the output of a decoder is a minterm. So if particular combination of, for a particular combination, the decoder will produce the corresponding minterm. So that we'll see and verify when we see the combination logic circuit for the 3 to 8 decoder. So here we can see what are the various combinations that can be obtained for the 3 inputs of the decoder, or 3-bit code that is present at the input, the 3 input lines. So here we have shown it as a table. Inputs for the decoder are given with the variable names x, y, z. So where x, y, z represents the 3-bit code that is applied at the input, and we have, since there are 3 bits, so we can have 2 power 3, 8 number of combinations for the 3 variables or 3 bits. So all those combinations are listed here, 0 starting from 000 to 111. So 8 combinations in the binary sequence. And similarly, at the other end of decoder, we have shown the outputs. So since it is a 3 by 8 decoder, so there are 3 inputs x, y, z, and the outputs variables are denoted as D0, D1, D2, D3 up to D7. So these 8 variables represent the 8 outputs, distinct outputs of the decoder. And you can see that for any particular combination, so how this happens actually, so we will apply certain combination of input, and this will choose a particular combination or values for x, y, z here, and for that chosen combination, one out of these 2 4, one out of these 8 outputs will go high, and the remaining will be 0. Or you can say that in general, one out of the 8 output lines will be active, and the remaining will be inactive. So here, if we have seen the first row, the 3 variables assuming bits 0 0 0. So this is one combination of the code. So this is one code produced by the 3 bits. So 0 0 0. Now So the occurrence of this code at the input of the decoder, 3 by 8 decoder, is represented by making the D0 output line high, and the remaining lines will be at 0. So when D0 equal to 1 means at the output of decoder, the code, the combination of bits present at the input of decoder is 0, 0, 0. So this is how the decoder will detect the presence of a particular code on its input line by raising one out of the 2 power n lines high. So here this 0, 0, 0 will make the D0 output line 1. Similarly, the another combination 0, 0, 1, this combination when detected by the decoder, makes the D1 output line 1. Similarly, when 0, 1, 0 is if this is the code applied at the input, then the D2 output line is made high. Similarly, when 0, 1, 1 is the code applied at the input, then at the output D3 line will be made high. And when 1, 0, 0 is the code applied at the input of decoder, then D4 line is made high. Similarly, for 1, 0, 1, it is the D5 which is made high, and for 1, 1, 0 of the input combination of bits, the D6 line is made high. Similarly, when the combination of bits chosen at the input lines is 1, 1, 1, when 3-bit code is 1, 1, 1, then the D7 output line is made high to indicate the code presented input is 1, 1, 1. So this is uh, also called as the truth table, as it contains both inputs and outputs for the 3 by 8 decoder. So here we can write, next we'll try to draw the combination logic circuit for the 3 by 8 decoder. And in order to draw the combination logic for the decoder, what we'll do is we have to get the algebraic equation or algebraic expression for all the output variables in terms of the input variables. So here you can see that the D0, you can see that D0, you can see that when I want to express the D0 function in terms of its input variable, you can see that D0 equals 1 only for one particular combination of inputs, that is x equal to 0, y equal to 0, and z equal to 0. And for all the remaining combinations, the D0 function is 0. So we'll write, so we can express the D0 function as sum of minterms, and since there is only one minterm, we can say that the D0 equals that particular minterm, and the minterm correspond to this x equal to 0, y equal to 0, z equal to 0 is, that we know already, we have learned all this. So it is the minterm corresponding to x equal to 0, y equals to 0, and z equals 0 is x bar, y bar, z bar. In the same way, we can write, we can express the D1. We can write the expression for D1. You can see that this is also written as sum of minterms, and you can see that the D1 function equals 1 only for one particular combination of x equal to 0, y equal to 0, and z equals 1, and since there is only one minterm, then d1 equals that particular minterm. It is x bar, y bar, and z. In the similar way, I can write Boolean expression for d2, d3, d4, and d5. Since you can see that all of these functions are equal to 1 only for one particular combination, so then those functions are equal to the corresponding minterm. So in the same way, I can go on writing the functions for all, and for d6, I'm writing for d6 again. In between, you check and verify, you write yourself the algebraic expression, Boolean expression, for the remaining functions d2, d3, d4, d5. And for d6, again you can see that this function equals 1 only for the particular combination of x equal to 1, y equal to 1, and z equal to 0. So here the minterm corresponding to this is x, y, and z bar. And similarly, I can write the Boolean expression for the d7, and you can see that this function is equal to 1 only for one particular combination of x equal to 1, y equal to 1, and z equals 1. So the minterm corresponding to this is x, and it is y, and it is z. So this way we'll be able to write the Boolean expression for all the outputs of the 3/8 decoder. So then you can observe that by seeing the Boolean expression for all the output variables, you can see that it requires and each expression contains only one minterm, that is one AND term. So this AND term can be obtained by using AND gates. So when the corresponding variables are applied as input, it produces the corresponding AND term or minterm or the corresponding output. So since we have 8 output lines, so 8 minterms are there, so we require 8 AND gates for the combination logic circuit, and for each of the AND gate, the corresponding variables present in the minterms will be the inputs. So here goes the combination logic circuit of the 3/8 decoder, and here we have 3 inputs x, y, z, where we apply the bits of the code that is to be detected by the 3/8 decoder, and we have 8 output lines d0 to d7. You can see that each as we have obtained the expression for all the 8 output lines d0 to d7. So you can see that each of the output can be obtained by using AND gate. So we have 8 AND gates here corresponding to the 8 outputs, and for example if d0 and d0, the inputs for this AND gate will be, as you can call it as 0th AND gate, and this is 1, and say this is 2, and this is 3, and this is 4, and this is 5, and this is 6, and this is 7. So for the 0th AND gate, you can see that the to produce this minterm and term x bar y bar z, the inputs must be x bar y bar z bar. And you can see that we are given with only the original variables in their original form, and to obtain the variables in the complemented form we can use the NOT gates 1, 2, 3. So for NOT gate 1 the input applied is Z and the output is Z bar, and for the AND gate NOT gate 2 the input applied is Y and the output is Y bar, and for the NOT gate 3 the input applied is X and the output is X bar for the NOT gate 3. So now we are provided with the variables in complemented form also. So in order to obtain the D0 output, apply all the X bar, Y bar, Z bar as input for the 0th AND gate. So X bar is applied and Y bar is given as the second input and Z bar is given as the third input. So it will produce an AND term corresponding to these three variables, that is X bar, Y bar, Z. Similarly, now all the 6 variables are available. Actually 3 in original form, 3 in complemented form. So for each of, to produce each output variable, output function, so we have seen the written the expressions, and according to this expression whatever the variable that is present, that the input must be given for the corresponding AND gate. So in that way we will be able to produce all the outputs by applying the corresponding input. So we'll see this for one more gate, that is 7th gate, and for 7th gate it has to produce the X, Y, Z product term or minterm. For this we require AND gate, and for which the inputs are, one is X, so X is applied, right, and Y is to be applied as second input, and no, Z is applied. So here X is applied. So X, Y, Z, three inputs are applied at the input of AND gate, and the output produces the product of X, Y, Z, which is the function D7. So in this way we can draw the combination logic circuit for the 3/8 decoder. And next now let's verify the working of this 3/8 decoder. So to verify the working of this 3/8 decoder, we will try to apply a few codes at the input of this decoder, that is on the input lines X, Y, Z. So if I see apply the code of X equals 0, so if I apply color, so if I apply this, we code 0, 0 and 0 at the input of the decoder. So then we will change this, take some other code. We'll apply 0 1 0. 0 1 0 is the code that is applied at the input. So what we know actually from the truth table, that when we apply 0 1 0 at the input, so that is this combination of bits we applied in the input are 0 1 0 is the code that is to be detected by the decoder, 3/8 decoder. And when it detects, what it will do, it will make the D2 output line high. And see, while explaining the working of this 3/8 decoder, this actually what happens when we apply the code 0 1 0 at the input. So once we applied 0 1 0 here, and the first gate, so 0 is applied at X input, and the output of this NOT gate 3 will be 1. And here on this line, this is X line, it will be 0. So we'll try to write first all the variables in their original line complemented form for all the 6 inputs. So y equal to 1, so y equals 1 only, and when y bar equals 0, which is produced by NOT gate 2, and z equals 0, and what z bar produced by the NOT gate 1, z bar equals 1 now. Now you can write the inputs for each and every AND gates, 8 AND gates, and after writing the inputs we can easily say what is the output of each AND gate. And you can see that for the 0th AND gate, one input is z bar. We can directly say z bar is going, so it is 1, and y bar is going, it is 0. And what is this third input? It is x bar. So this is also equal to, no, x bar equal to 1. With x equal to 0, x bar equals 1. So x bar, the third input line, is equal to 1 for the 0th AND gate. So we'll write the outputs later after writing inputs for all the remaining AND gates also. So for this AND gate 1, one of the input is Z, and it is equal to 0. And the second input is y bar, that is also equal to 0. And the third input is x bar, which is equal to 1. So these are the inputs for first AND gate. And second AND gate, one of the input is z bar, which is equal to 1, and second input is y, which is also equal to 1, and third input is x bar, which is also equal to 1. And for third AND gate, inputs are z equal to 0, and what is this, y, that is equal to 1, and third input is x bar, that is also equal to 1. And for fourth AND gate, inputs are z bar equal to 1, and what is this, this is y bar equals to 0, and x, which is also equal to 0. and for fifth input is add equals 0 and y bar equals 0 and x equals 0, and for sixth this is z bar equals 1 and this is y equals 1 and this is x equals 0, and for seventh and 8th input is z equals 0 and this is y equals 1 and this is x equals 0. So we got inputs for all the 8 AND gates. So now we start writing the outputs of each AND gate. So for this one of these, we can easily say that for AND gate, if at least one of the input is 0, the output is 0. Output is 1 only when all of the inputs are 1. So for this AND gate output is 0 by that, and this output is 0, and for this AND gate only all the inputs, for the second AND gate only all of the inputs are 1, so the output is 1. And for you can see the remaining AND gates also at least one input is 0, so the outputs of all these AND gates are 0. Now you can see that out of all the outputs only one output is non-zero, that is D2. That is this non-zero output line. Now it is detecting the presence of 0, 1, 0 code at the input of decoder. So in this way we can see how the various other codes are also detected by making the corresponding output line high by the decoder circuit. Next we will look at some important applications of the decoder circuits in digital electronics. So in digital systems, the decoders are used in digital displays and some data demultiplexing and digital to analog converting, and one important application is memory addressing. And you can also see that as each output of the decoder is producing one minterm for the given n variables, it is able to produce the 2 power n minterms. And you can see that any Boolean function of n variables can be expressed as the sum of its minterms. So since our decoder is producing all the minterms, then the function can be realized by using this decoder circuit by clubbing the required number of required minterms for the function. So for example, if I have a 3 variable function and I use 3 by 8 decoder, so this decoder produces all the 8 minterms, but my function expressed as sum of only 4 minterms. So what you have to do, out of the 8 minterms produced by the decoder, you have to select the minterms which are present in the expression of the function, and you have to use an OR gate to sum all the minterms that are required to realize the function. So now the function can be realized in the sum of minterms form by using our decoder, as it is producing all the minterms for n variables. So this is also one important application of the rebiite decoder. So this is all what we have learned about the decoder. You can see that that's what we have did. We define what is a decoder, and in general way it can be said that it is a combinational logic circuit which detects a binary code present at its input and indicates the presence of that particular code by rising by a specified output level. So if the binary code has n bits, then the output of the decoder may have maximum of 2 power n output lines or output levels. So by that our decoder may be called with the names n to m line decoders, where m represents 2 power n, or and they are also called as n by 2 power n decoders, where n represents the number of input lines or the number of bits present in the code applied at the input of decoder, and 2 power n represents the number of distinct output lines. And in particular we have started looking at the working of the 3 by 8 decoder, and we define what is 3 by 8 decoder, and we have shown how the 3 by 8 decoder is formed by using a simple truth table consisting of the inputs for the 3 bits that are applied at its input and the 8 outputs that are available for the decoder. And there we observed that for each unique code applied, distinct code applied at the input, only one out of the 8 output lines goes high, and the remaining will be at 0. So indicating the presence of that particular code at the input of the decoder. And after that, from the truth table, we'll be able to draw the combination logic circuit for the 3 by 8 decoder using our basic logic gates. And to draw that, we have written the expression for each of the 8 outputs, and we have seen that each expression is a minterm of the input variables either in original form or in complemented form. And after obtaining these expressions, we have drawn the combinational logic circuit for the 3 by 8 decoder, and we explained the working of the decoder by applying one particular code at the input of the decoder. And we have shown that only one output line corresponding to that particular code applied at the input will go high, and the remaining output lines will be at 0. And this completes the working of the 3 by 8 decoder. And after that, we have looked at some important applications of the decoders in digital systems like D2A converting and digital displays and data demultiplexing and memory addressing and also the realization of the Boolean expression for any function as the sum of minterms with the help of decoders. And the further information on the decoders, you can go through the reference textbooks mentioned in our curricula. And with this we complete the discussion of decoder and the working of decoder and a particular decoder called 3x decoder and the applications of the decoders in general. Thank you.